All right, here we go. This is the chemical lab reactions, little lab we did, the 5-reaction lab we did the other day, and I'm going through the questions and the answers, and some of the wording might be a little bit confusing, so let's go through it and make sure you understand. So what is a chemical reaction? I believe someone should be able to come up with a page number for that for me, where that is in the textbook. But it's the making and breaking of chemical bonds, which really doesn't tell you much if you don't understand what a chemical bond is. A chemical bond is either ionic or covalent, which means it's either transferring electrons or sharing electrons, right? So you can talk about a chemical bond or a chemical reaction as being the rearrangement of electrons. Somebody look that up and find it on the page for me in the textbook, if you would, please. Okay? So the next thing is, what are the indications of a chemical reaction? I forgot to highlight this in red, but color change, production of a precipitate, production of a gas, production of heat and or light. Okay? And what page is that on, somebody? Tell me the page number. Okay? And then we're here on number 3, it says, what are the 5 main types of chemical reactions? Synthesis or combustion, same thing. Decomposition is the opposite of synthesis, which would be decomposition, right? Yes? 251 for which? 261, all right. Thank you. Page 261 in the textbook, okay? And so we have synthesis, which is like normally what you're going to see is 2 reactants and it produces 1 product, okay? That's also sometimes called combination, depending on the textbook. Then decomposition is the opposite. Usually what you see is 1 reactant and it breaks down into two products. But like we saw before there, where we were breaking down that iron 3 oxide on that other reaction we were just working on, I mean, that is technically a decomposition of iron 3 oxide, although we had 2 reactants, right? So you got to be careful there. But normally when they're checking you on a test, particularly a standardized test, they're going to give you the most obvious, all right? So that's what you look for, okay? Then the third type is the single displacement. The key with the single displacement is they're almost always asking you like 2 metals, okay? 1 metal is in solution, bonded to an ion, right? Or it was bonded to an ion, but it's in aqueous solution. Our classic example is we add zinc to copper sulfate, okay? Well, zinc is higher than copper on the activity series, so the zinc will displace the copper, and we'll end up with the zinc ion and the sulfate ion, and the copper will gain those 2 electrons and obtain a 0 charge, and it will precipitate out, so it falls out. So we have a single displacement. Double displacement is a little bit more complicated, and normally what you'll see is 2 salts dissolved in water, okay? When we say salts, we're talking about ionic compounds, cations and anions dissolved in water. Now the way the double displacement reaction starts is you have 2 separate containers, like we did in our reaction 3, right? And I believe we had potassium iodide and lead nitrate, okay? And you have them in separate containers, and then you combine them. And what happens when you put the 4 ions together, none of them will stay together. The water dissociates all of them except 1 combination, and that would be the substitute, right? In our case, the example we had, the lead bonded with the iodide, and the water did not dissociate it. So the lead iodide stayed together and precipitated out. It also happened to be bright yellow, but that's double displacement. And then the 5th type is combustion. And combustion, the biggest problem is, I think because I overemphasize it, is people are looking for CO2 and water as the products. Well, CO2 and water are the products of combustion of organic materials, carbons and hydrogens, right? Particularly hydrocarbons, like in your automobile, octane, C8H18, right? Okay, but you can have oxidation of metals, like we did in our lab, in this lab. The addition of oxygen to magnesium produces magnesium oxide, no CO2 and no water, right? But still combusted to magnesium, okay? Now, the next questions here are just asking you what are the potential dangers here, and we always like to do this before we do a lab, so you have your, give you a little heads up on it. Well, the magnesium burning, besides actually burning yourself, because it burns pretty hot, burn your skin, is it's an eye danger. It's so bright. It'd be like looking into a camera flash bulb continuously. Not good, right? Lead is obviously poisonous, and then open flame, you could burn yourselves. And you got to watch burning your hair too if you have any. Okay. And then this one right here, we're not gonna get into this with what equipment do you need for each of these reactions. You just need to read through the procedure, and you can read the equipment. And it's a good check for you to see that you understand what the equipment is what it is. It's a good idea that you know the difference between a famous one that's missed on the SOL is the difference between a crucible and an evaporating dish, okay? And things like that. And watch glass, people often confuse watch glass with evaporating dish with crucible and whatnot. So you want to make sure you don't make those crazy mistakes, because those are like easy questions. You don't want to miss those, okay? Now as we move on down, it says what indications did we have, or what changes did we see in these reactions? Well, in the first reaction, where we dropped the zinc into the copper 2 sulfate, the copper 2 sulfate is the blue solution. And we dropped the zinc pellet in there. It looks like a little silverish or metallic looking button or pellet. We dropped that in there, and it takes a while for it to happen. It's not real fast, but what happens is the zinc, because it's more reactive than the copper, starts to force its electrons onto the copper ions. The copper 2 ions are in solution, and so they pick up the electrons from the zinc atoms that are in the pellet. And so as soon as the copper picks up the 2 electrons, it loses its 2+ charge, and it can't stay in solution anymore. The water drops it. And where does it drop it? Well, right on top of that zinc pellet, because that's where the zinc is. Well, what happened to the zinc atom? The zinc atom became a zinc 2+ ion, and it goes up into solution. So they switch places. Okay, the zinc replaces the copper. And as a consequence in this case, zinc chloride is clear. And so over the course of time, what you see is that blue solution becoming clearer and clearer and clearer. Now, in the calcium sulfate reaction, okay, we add zinc to calcium sulfate, and what happens? Nothing. Nothing. Zinc is lower than calcium on the activity series, okay? So the zinc cannot displace the calcium, and so we have no reaction, and that's the way you'd write it. Okay, go ahead and write out the no reaction. Up here, we had the solid zinc, and we add it to the aqueous copper 2 sulfate, and because the zinc is higher than copper on the activity series, we switch places. And of course, you could write this out in the ionic form, but you shouldn't need to, because it's fairly straightforward. Here, the copper falls out. Okay? Down here it's asking what are the appearance of the reactants before and the products after each reaction takes place. Well, in reaction 3, what we had was we had what did we have? We had lead nitrate and potassium iodide, okay? And both of those are fairly clear solutions. As soon as we put them together, we poured a little bit of one solution into the test tube first, and then a little bit, I think about a milliliter of the other solution into the same test tube. As soon as we pour them together, we see this brilliantly bright yellow substance form in the test tube. And if you wait long enough, it's hard to see it immediately, but you got to wait a little period of time, and you'll see that yellow substance fall to the bottom. Okay? If you wait long enough, all of that yellow will fall to the bottom, and that yellow is the lead iodide. So what I wrote down here, and you can write it any way you want to, but I said 2 fairly clear solutions, and at the end we have a bright yellow precipitate. It's hard to see if anything's clear in there after that precipitate forms. Okay? Any questions about that? Miss Fuel, you still awake? Okay. Alright, so we move on down here. And this is asking us about reaction number 4. And reaction 4 was the combustion reaction, where we put the little warming candles under a 100 milliliter beaker and under a 400 milliliter beaker. And of course, just as you would suspect, in the 100 milliliter beaker, the candle goes out much faster than it does in the 400 milliliter beaker. Okay? And the reason is why? Well, oxygen is what we're concerned about. When you say air, you got to be careful now. What you're talking about is oxygen, and the the technical phrase in chemistry is oxygen is the limiting reactant. What's the limiting reactant? What is the definition of a limiting reactant?
The reactant that's limited?
That's
the word.
it's the reactant that you run out of. Okay, so we ran out of the oxygen in the smaller container because oxygen's about 20% of the atmosphere, and theoretically 20% of the 100 milliliters, about 20 milliliters was oxygen in the 100 milliliter beaker, and in the 400 milliliter beaker, how many milliliters was oxygen? 80. 80. Okay, so we had 4 times more oxygen in the large beaker than we did the small beaker, and the burnout time should have been about 4 times greater. Okay. Now here it says record the appearance of the reactants before and the products after each reaction takes place. Well, in number 5 we're talking about magnesium. So we took magnesium ribbon, and that's kind of a silver gray, certainly metallic looking little strip of metal, and we put that baby in the Bunsen burner and lit it up, and it gives off an extremely bright flame. But then what you have left is this white, it's almost pure white looking ash. Well, that's magnesium oxide. Okay, that's almost pure magnesium oxide, and so we had a drastic difference. There's a lab that some folks do with that. You try to measure the mass of the magnesium before you combust it, and then measure the mass of the magnesium oxide. It's very difficult because this white ash is so hard to contain and measure. Okay, but that's the difference there. All right, so now here you should be at the stage where you have no problem balancing these equations. You got to be careful with these states. You got to write the states down, particularly if it's a double displacement reaction. It's critical. It's wrong if you don't write down whether it's solid or aqueous. Okay. So here in the first reaction 1, we had a single displacement reaction with copper 2 sulfate in aqueous solution, and we're going to add solid zinc to it. Now that solid zinc means pure zinc, which means it has what charge or what oxidation state? 0. Okay. It's got all its protons and all its electrons, and they happen to match, right? So it has a 0 charge. Therefore, it's not going to dissolve in water, right? But because the copper 2 sulfate is in aqueous solution, means that you have, what that means is that you have copper 2 ions and you have sulfate ions, and that's why they dissolve in water. Well, what happens is the the zinc displaces the copper because it's higher on the activity series. Because the zinc and the copper both form 2+ ions, the equation's balanced as it's written. Right? Any questions? Now, here, where we're talking about calcium sulfate and zinc, we have no reaction. Because if you look on the activity series on page 286 in your text, you'll see that zinc is above copper, so it will displace it, but it's below calcium, so it will not displace the calcium. That's a guaranteed. You will guaranteed to be asked if you understand that on your state SOL. Okay. Now here we're looking at a double displacement reaction. Reaction number 3, where we have the lead nitrate in aqueous solution and we have potassium iodide in aqueous solution. Okay, and so we're going to, if we have an insoluble salt, and we do, which is potassium iodide, this should be a subscript, potassium iodide, then we have a double displacement reaction. What happens is the potassium just switches place with the lead, the potassium and the lead switch, right, and we end up with potassium nitrate and lead iodide. However, unlike this one up here, the potassium's a 1+ and the lead's a 2+, so you got to do a little manipulating to get it to balance. Okay, you're going to need 2 potassiums and 2 iodides over here, and over here the 2 nitrates leave you the 2 nitrates over here. Okay, so it balances itself if you write the equations correctly, and that's where a lot of folks have trouble and don't realize it is it's in balancing the equation or writing the formulas actually. It's difficult if not impossible to balance an equation one or more of the formulas, chemical formulas, is improper, incorrect. Okay? Any questions about that? No? Alright, so we did the double displacement. And now we're looking at a combustion reaction here. Reaction number 4 is combustion. And we took this candle wax, and what we did is we assumed that that candle wax, the wick is just there to keep the flame, okay? And what's really being burned, that's why you notice a candle can burn for hours and hours and hours and never burn the wick up. Well, it's because what you're burning is the wax. You burn very little of the wick. Only the wick, as it gets up above and gets unsaturated by the wax, do you burn the wick up at the top, okay? But anyway, interesting formula here, C25H52, and what that shows you is these carbon chains get longer and longer and longer, then the carbon molecule goes from gas to liquid to solid. Well, here it is as a solid. And we're going to burn this baby up. And to balance it, what we did here is we tried the simplest solution first and put the 25 carbons in front of the 25 CO2s. And then we have 52 hydrogens, so we put the 26 in front of the H2Os, okay? And so that balances our carbons and our hydrogens, and then we just check to see, can we balance the oxygen with that configuration? And as it turns out, we end up with an even number over here on the product side, which means it's easy to balance on the reactant side because it's O2. It's an even number, right? So we've got 25 times O2 is 50 oxygens here, and 26 times 1 oxygen here is 76. So then 38 O2s will give you 76 oxygen atoms. 38 molecules of oxygen give you 76 oxygen atoms. Miss Briggs, you sleepy? You're famous. You're now on YouTube. So here we have magnesium, our last reaction, reaction number 5, and what we're going to do is we're going to provide a little activation energy there with the Bunsen burner and get the magnesium hot enough, right, to reach the activation energy, and at that stage it's going to combine with the O2. Now it has enough energy for the O2 molecules to break apart, and they will bond with the magnesium. And it also, in the meantime, gives off heat and a very, very bright light. The product is the magnesium oxide, the metal oxide. Okay? This is a classic example of a combustion of a metal, right? Now, because the magnesium forms a 2+ ion, yes, it's in group 2, so it always forms a 2+ ion, and oxygen always forms a 2- ion, right? It's balanced as it looks, okay? Okie dokie. Questions about that one? Alright, let's see what we got down here. This one says, what signs did you observe that indicated a chemical reaction was taking place? Okay? And I don't know if I'm specific enough or not, but what happened in reaction number 1, where we put the zinc in the blue copper 2 sulfate? We had a color change and a precipitate. What was the precipitate? Reaction 1. The copper falling out. And where did it fall out? It fell right onto the zinc pellet, which is kind of strange looking because we had that metallic zinc pellet look kind of like a little button, and then as time goes by, it starts to look brown and fuzzy. Well, that's the copper. That's the copper falling out right on top of the zinc. Okay? Mr. St. John, wake up back there. You're on YouTube. Millions of people are looking at you, watching you sleep through chemistry class. Okay? Reaction number 2, we add zinc to calcium sulfate. Okay? And what happens? Nothing, because zinc is lower than calcium on the activity series. Okay? So you want to make sure, you want to make absolute sure that you know to look. I'm going to put the page number here, page 286, activity series. Now, I don't keep writing this activity series down here for you to go look at the table. It's the reading on the page, okay, that I want you to do. That's where you would read up on the explanation of metal reactivity. Okay? Now here, reaction 3 is where we took the lead nitrate and combined it with aqueous lead nitrate, and we combined it with aqueous potassium iodide. And what happens is when the lead 2 ions run into the iodide, which are 1 negative, okay, that gives you an unbalance, so you have 2 plus and 1 negative, so it takes another iodide ion, so now you have 1 lead 2 ion and 2 iodide ions. Then once that lead 2 iodide forms, the water molecules do not dissociate it, okay? So the net charge on the lead 2 iodide becomes 0, and it will not stay in the solution. It falls out to the bottom, okay? So this, you look at, this would be page 860, okay? This is the solubility tables. And if you look in our solution chapters, you'll see solubility rules, okay? So what we saw there was a color change of very, very bright yellow precipitate. The change we saw here in the candle thing is we actually see the flame, right? And you can feel the heat. And there was some other products being produced. You could see a little bit of smoke being produced. It burns, the candle burns pretty clean, but you could see a little bit of other things coming off of it, right, Ms. Fuel? Okay. Now here on reaction number 5, where we set off the magnesium, we combine the magnesium with oxygen. We need to provide that activation energy, which came from the Bunsen burner again, okay? We can see this thing burning. We can feel the heat from it, and you can very easily see the smoke. But here, in addition, the product over here is an obvious white ash, very different than the reactant we started with. Over here, once the candle goes out, things settle down a little bit. You're looking in the beaker, it looks like there's nothing there, but actually what you've done is you've replaced the oxygen in the beaker with a quantity, a molar quantity that's the correct ratio of CO2 and water inside that beaker. And as it cools, you'll see water vapor form in that beaker, okay? All right? So here, question number 2, this is like a restatement right here, this is talking about reaction 1 and 2. It says, why did 2 not occur, but reaction 1 did? Well, remember, 1 was the zinc and the copper, and 2 was the zinc and the calcium. The reason reaction 2 did not occur is because the zinc is less reactive than the calcium. Page 286 again. That's your activity series. The zinc is more reactive than the copper, so the single replace reaction takes place, okay? And here it says, see the activity series of metals, page 286, okay? Any questions? Anybody have any questions about that? All right, question number 3 says, what is the chemical name for the precipitate that you observed? Lead 2 iodide, okay? Lead 2 iodide. You have to use the Roman numeral for lead. Now that is a little bit of an exception to our naming rules, because lead and tin both are not in the transition block, right? They're not in the D block. They're actually in the P block. They're classified as other metals, okay? However, because both tin and lead, Miss Fuel, can have a 2 plus or a 4 plus charge, you have to designate which one you have, okay? Lead 2 or lead 4, right? In the name. In the formula, you don't, because you always know the anion, right? So really the key is understanding the anion, because in the formula, you can figure out what the charge on the cation is. In the name, you have to be told. And the way you're told what the charge on the cation is either from its position on the table in the main block or with a Roman numeral. And then you got to make a footnote, or if it's zinc or cadmium or silver, they always form, zinc and cadmium are always 2 plus, silver is 1 plus, okay? So that's just a little detail you got to remember, okay? Now this one right here is really getting us into chapter 9. This is a stoichiometry question. There's 2 kinds of stoichiometry. There's composition stoichiometry and reaction stoichiometry. And reaction stoichiometry is what we're starting to focus on now. Composition stoichiometry is just how many moles are there in this mass of a substance. or what would the mass of this many moles of a substance be, right? In other words, same substance. If substance A has a mass of such and such, how many moles of substance A do we have, right? In reaction stoichiometry, where we're going and much more interested in Chapter 9, where we're talking about, we're actually able to convert moles of substance A to moles of substance B. Very interesting. The only thing we need is the balanced chemical equation, okay? And this is an example, and it's kind of a good one because it starts out with a very, very basic idea that you learned probably way back in middle school. This thing says that if we have 6.20 grams of lead 2 nitrate and 6.22 grams of potassium iodide, how many moles of lead 2 iodide must we have? And it gives you the also gives you the mass of potassium nitrate. Well, what you know is that the mass on the reactant side of the equation's got to equal the mass on the product side, right? Everybody know that? So what's the answer? Mr. Rapinski, you're absolutely right. You take the 12.42 total here. You know this has got to be 12.42. You've got 3.79. You subtract it, and the difference is 8.63. And you say 8.63 grams. Okay? Now that's due to what? Nope, that's not even, well, in a way, with the way we're using it, stoichiometry just means calculations with chemical substances, okay? So I guess that is a form of stoichiometry. But how do we know that's true? How do we know that basic premise, that if we have 12.42 on the reactant side, we've got to have 12.42 on the product side? The law of conservation of mass. The law of conservation of mass, okay? You learned it many, many moons ago, okay? But now let me show you the way we're going to use the stoichiometry, okay? Let's take the mass of this potassium iodide right here, okay? 6.22 grams of potassium iodide, and convert that to moles. And you know that we're going to take the unit that we're given, and that is going to be in the denominator. That's going to be in the denominator. And what we want to convert to is going to be in the numerator. So we want moles of potassium iodide. Okay? So hurry up and do that calculation real quick. Moles of potassium iodide. Okay? And then what we're going to do is we're going to say, okay, because we have this balanced chemical equation, we're going to convert moles of potassium iodide to moles of lead 2 iodide. Now that's a little bit different than math, right? Okay, where you've got 4 variables and all you need to know is one of them and you can calculate the value of any of the others. That's chemistry. That's why people love chemistry, Mr. Gonzalez. You were wondering why, right? That's why. So, what we want here then is moles of potassium iodide, because it matches the moles of the unit of where you're going, okay? And so what is the molar mass of potassium iodide? 1 mole of potassium iodide per 39.10, right? Oh, sorry. That's potassium. It's 166, I'm sorry. Isn't it? It's 39.10 plus 126.90. Isn't it 166.00? Yes? And so that gives us how many moles? Huh? We want to go 6.22 divided by 166.00, and that gives us 0.03747. 0.03747. And I'm going to extra significant figures because I don't want to round at each step. Now, here's the critical issue right here. How do we How can we go from moles of one substance to moles of a different substance? We do that with the balanced chemical equation. This is moles of potassium iodide, lead 2 iodide per moles of potassium iodide. Where do we get these figures? From the balanced chemical equation. I need a new color here. From the balanced chemical equation. So, we have 2 moles of potassium iodide to the understood 1 mole of lead 2 iodide. So we divide our answer by 2, and what do we get? .01874. I got 735. Right? Yes? Everybody agree with that? Now, we want to end up with, what we want to end up with is grams of lead 2 iodide. So what are we going to multiply this by to end up with grams? Miss Briggs? We're going to multiply by grams of lead 2 iodide, right? Per mole. Yes? Yes? What is the mass of lead 2 iodide? 207.2 plus 126.90 plus 126.90, and I believe it comes out to 461.00, does it not? Huh? 4.6100 is the mass of lead 2 iodide, right? Okay. And so we're going to multiply that by the number of moles of lead 2 iodide we had, and it better come up to the same thing we got here, and it did. And so here and here, and so what we're showing you is we're not violating any natural laws here, okay? This is just a shortcut. It's not necessarily a shortcut. What it is a way that you can calculate the quantity of any substance in a balanced chemical equation if you know the quantity of any other substance, okay? And we're going to find that that's true if you know the quantity of the substance in mass, in moles, if it's a gas, in liters, right? And so it's a very, very interesting and valuable tool that we're working on, okay? Now, these last questions are pretty straightforward here. Boom, boom, boom. Why did the candles go out at different times in reaction 4? Because we ran out of oxygen. Oxygen was a limiting reactant. In reaction 4, what filled the beaker? The chemical names of what filled the beaker. Well, CO2 and H2O, carbon dioxide and water, or dihydrogen monoxide, right? Everybody got that? Reaction 4, is this considered to be endothermic or exothermic? It's considered to be exothermic, and the reason is the obvious reason is we know heat was generated, right? If you felt the beakers, you would feel the heat. But the chemical answer is that where do you see more potential chemical energy? In the candles or in the smoke and the CO2? In the candle wax, right? So the products have less potential energy, right, than the reactants. Same thing with number 5, okay? Number 5 was burning the magnesium. Both those reactions are exothermic, okay? Question number 10 here says, okay, if you have a reaction that produces 2 products, what kind of reaction is it? Well, it could be decomposition, could be single displacement, could be double displacement, right? And it could be combustion. Yes? How about a reaction that only produces one product? I think synthesis is the only one, isn't it? Well, I don't know. You know, we just burn that magnesium, and if that were perfect combustion, all we would have is magnesium oxide. So combustion might in there. I'm not sure I like that question. C says if you have two reactants, then you could have a synthesis reaction. Could be single displacement, could be double displacement, could be combustion. Right? And then if you have one reactant, I don't think that's going to have to be decomposition. If you have one reactant and we have a chemical reaction, I think that's going to have to be decomposition. Number 11 says write the net ionic equation in the lab, and remember to label the reactants and the products as solid, liquid, or aqueous solution. Well, here you had lead nitrate, lead 2 nitrate, potassium iodide, and potassium nitrate, and lead 2 iodide. Okay, so you got potassium iodide and potassium nitrate on one side, lead nitrate, and not on one side. You got lead 2 nitrate and potassium iodide on the reactant side, potassium nitrate and lead 2 iodide on the other side. So the cations switch places. The total ionic equation is here. The total ionic equation is here, where you write it all out. Okay, so you got the lead 2 ion in aqueous solution, the 2 nitrate ions in aqueous solution, the 2 potassium ions in aqueous solution, and the 2 iodide ions in aqueous solution. On the product side, you still have the 2 potassium ions and the 2 nitrate ions, but the lead 2 ions and the 2 iodide ions bonded together, and the water does not displace them. So how do you come up with the net ionic equation? You cancel the ions that you see on both sides. You see 2 nitrate ions on the reactant side, and you see 2 nitrate ions on the product side. You see 2 potassium ions on the reactant side and 2 potassium ions on the product side. Okay? So the net ionic equation is only what's left. And the only thing you have left here is the lead 2 ion, the 2 iodide ions, and they combine to produce the lead 2 iodide. And that is only a double displacement reaction if one of the products is insoluble. Or there are some cases where one of the products would be a molecule, most likely water, and most likely that'd be a neutralization or an acid-base reaction. And sometimes double displacement reactions can involve the production of a gas. But the bottom line is one of the pairs of ions, cation, anion pairs, has to leave. Otherwise, you'd end up with the same ions floating in solution that you started with. And that's what we call a no reaction. Yes? Okay, any questions about this? Everybody got this written down? Okay, well, everybody should ace the quiz. This is what the quiz is on, is this right here. Okay, questions? I'm sorry?